Thank you very much. It's a great pleasure, great honor to be here. My thanks to the organizers. And let's get started. So we'll talk about topics that have kept me busy and intrigued for the last 5 years or so, or a little bit more. Signatures, log signatures, moments, cumulants, and then the final part, putting them somehow together. So what is a signature? This has been quite successful in the last 5 years or so. The idea is not new and simple enough. So you have some path, high dimensional, d-dimensional, and for now, let's say it's smooth, but as long as these iterated integrals are defined, you may as well think they're bounded variation to keep it simple. And so let me define the indefinite signature. Indefinite means there's a little time t that you're still willing to have running. And so what you get here with these iterated integrals are just a lot of objects that you can put in this big space here that's known as the tensor algebra. And I am actually a bit shocked that my slides are, let's see how bad it is. Anyway, the two parentheses missing here. This is the tensor algebra. As a linear space, it's clear, but you have a natural algebra structure there, which is basically it's the calculus of power series in D non-commuting indeterminates. So the calculus aspect here is quite easy. And if you think about it, this signature, if you take a derivative here, then you just take off one integral here at a time. And so you can conveniently rephrase it, this whole thing here, give it a dynamic description in terms of a simple differential equation. It's a linear differential equation in the state space, which is this full tensor algebra. And when I put a 1 here, I mean the subspace where you start with scalar 1 here. So this is where you start. And so you have a very simple, somewhat linear differential equation that describes you this signature. So with that power series calculus in place, you can define the exponential, you can define its inverse, the logarithm, and I will, what follows, I will just drop these stars here. So many people would write here tensor product, but I want to keep it separate from the tensor product I use later. So it's just the concatenation of tensor product, and I will drop it. Now, it's a fruitful notion, and about 10 years ago, a little bit longer, it was used very successfully in combination with state-of-the-art machine learning to create a Chinese character recognition algorithm that turned into some award-winning app, actually. More recently, it was used to create financial data, somehow model-independent, data-driven finance. There was a prestigious industry award that went in that direction. And just to give you a little bit more of somehow why is it mathematically interesting, that these signatures, if you think of the definite signature, so now let's, fix 0, 1 as a time interval. And if I give you this fixed tensor series, it tells you a whole lot about the underlying path. So it determines essentially, there's some disclaimers that I want to maybe talk later about. It essentially determines the path. And that was understood by Chen in many years ago for smooth paths. There was a famous paper by Terry and Ben Hambley for PV paths. It was an Annals paper 2010. And there was an extension here to geometric rough paths. But I will not define this rough path now at this moment. OK, so once you have the signature, this is somehow this long sausage in the tensor algebra, you can switch to the logarithm, and that's called the log signature. And that you can compute the first few things. This is how it looks like. Not much here. This is still somehow the increment from x from where you start to where you want at time t. And then the higher ones, you see these commutator brackets popping up. So this has an interpretation of the area, but I'm not going to draw pictures here. And then on it goes. There's a lot of structure here. This is a so-called Lie series that pops up here. I'll make this more precise. And let's understand what is the structure of this log signature dynamically. So again, I want to understand, is the differential equation here? And the answer is, well, you can just rewrite the linear differential equation driven, so that you have for the signature. You can rewrite it as a differential equation or try to rewrite it as a differential equation for this log signature, the first thing you do is you rewrite this one, you put the S on this side here. Remember, non-commutative algebra computations. This is just a rewriting here. And in a commutative setting, you just use calculus here, and that everything is the way you would like it. And then you have LT, and this I'm very embarrassed that I didn't check the slides close enough to see this cut here. I think we'll be fine. So the answer to this is at least 100 years old. And I think there are even people previous to Hausdorff who understood this. So when you want to understand, so remember X was somehow this reference path, and L is the log signature. If you rewrite, this is just a rewriting of the linear equation that we had for the signature. And if you want to understand what this is here, then you have to understand really, in a non-commutative setting, how the derivative of the exponential function looks like, and that leads you to this expressions here, where G is really power series. I mean, this is totally explicit. I think it's the expansion of Ex minus 1 divided by X, or Z. And here we use this to put the add operator. So this is just the linear operator that you get by you see it here, by left bracketing whatever you put in with this L here. And then you iterate this here in this power series. This gives you this iterated commutator series here. So this is good, but not quite what we want, because you wanted an equation for L dot, and here it's still somehow, with this prefactor, so you can get rid of this by switching to the inverse, also on the operator level. And then you have here, for an explicit series here, the Bernoulli numbers that come up, you have a differential equation that tells you dynamically, given X, what is the differential equation you solve for the log signature, and here it is. Okay, nothing new. Once you have this equation here, and remember we have this graded structure, so X is d-dimensional, and so this bracket here is the commutator bracket. So if I do an expansion here of L here, I decompose it in tensor levels, then this equation here translates immediately to a recursion, and this is called, in this context, so this is one instance, if you want, of a Magnus expansion. So this is the first two explicit. If you want to write out the general term here, you can even find this on Wikipedia. There's a whole fan club on these Magnus expansions. So here, as a survey 10 years ago, must have 1,000 citations or so. So why is this a good idea? Why switching to the log? Well, some reasons, I give you two here, is what we have really done here from a differential geometric perspective. We have developed a path in the Lie algebra in the Lie group. And so when you truncate here, when you do this picture here, switching to the L, switching to Lie algebra, when there's a linear space, when you truncate, you don't fall off. Whereas in the group, if you do something silly, you just fall off. So this respects the geometry, and so you're still, in some precise sense, group-like when you do these truncations here, when you approximate. The other one is sparsity. Let me tell you a very simple computation here. So V here is a d-dimensional vector, a one tensor. And I think of a path that runs a straight line in that direction. And I compute the signature of that path. So if you remember iterated integrals, etc., what you get is this here. And if you think in the tensor algebra, you can just, you can put them next to each other, but you can also add them up in the tensor algebra. It's the same thing. This is the exponential function in the tensor algebra. And if you take the log, you take off this exponential, and you're back to V. So this has to do with sparsity. It's a good idea, or it can be a good idea, to switch back to the log here. And here are some other citations that I'm not going to read out. Here's some. So again, it's a very useful concept. Now, here's a recent result. We know that these log signatures are Lie series. And this Magnus expansion makes it explicit. And you can ask, well, could it be that this Lie series happens to be finite? Well, then let's call it a Lie polynomial. And can it happen? Sure. We just have seen an example. You take the signature of this straight line, that was the exponential, the log takes off the exponential, you're back to this direction vector V, and that's clearly a Lie polynomial, even of degree 1. Here's a theorem. If the log signature of a transform of some PV is polynomial, then it is necessarily of degree 1 series trivial. then you're necessarily in this setting here, okay? Let me show you how to prove this, a sketch here. The proof, I think, is interesting because it uses ideas from rough paths, whereas the problem has nothing to do with rough paths. Up. I'm too quick here. Up. Help. Getting there? All right. So assume the log signature is finite. This is the assumption, it's finite. Okay? So let's give the name, let's call it A. This is a Lie polynomial of degree n, right? And so let me cook up a path now. I look at the tensor exponential of t times A, so I run somehow straight in the Lie algebra and then exponentiate the whole thing. This is that way I'm group-like. Everything is truncated level n here, so I'm in the truncated level n tensor algebra. And if you know what rough paths are, this is an example of a genuine, or this is a, really a non-trivial rough path here, geometric by construction, because you're group-like by putting the Lie algebra element in the exponential. And you have this graded regularity that's part of the definition of a P rough path. You don't have to know what a rough path is. If you don't know, don't worry about it. Just take it that this defines a genuine geometric P rough path with a certain regularity parameter P that happens to be the level n here. Okay, so this is assumed non-zero. And so the signature of, there's a notion, so we haven't talked about signature as rough paths, but take it on trust that you can extend the notion of signature that we defined in the beginning. There's a very natural way to extend it to geometric graph paths. Essentially, geometric graph paths are limits of smooth paths lifted in certain metrics that this passes on, okay? So the signature of that rough path, you can compute it. It shouldn't be too surprising. It's the tensor exponential of A, but now here in the full tensor algebra. On the other hand, you can take the original path X. Remember, this was a d-dimensional PV path. You can also lift the geometric graph path. How? Just by doing the indefinite signature lift. Right? So by construction, these two rough paths have the same signature. There's some consistency result. The signature of this canonical lift is the same as this one. They have the same signature, definite signature on 0, 1. Now, you remember this result I mentioned by Bohiraccio et al., 2015. They must be the same as rough paths, essentially the same. And so now I can come clean on this. Essentially means if you look at them, tree-reduced mode parameterization. This, these are iterated Stieltjes-type integrals. They never tell you anything about the parameterization, so you have to quotient that out. Starting point, trivially, you can't recover, you don't care. And this tree reduction, this is somehow non-trivial because there are certain paths, non-trivial paths that have trivial signature. Namely, when I go in this direction and I backtrack precisely, if you think what how the signature is defined with ODEs, you see immediately this leaves nothing left. The signature is just the one element. And you can iterate this picture and go out and left and backtrack and go out again and backtrack, and so you can build these trees. And they will all have trivial signature. So these you have to weed out or quotient out. This is what I mean, tree reduced, and then it's the same. And this is also in the statement here, when I say essentially, this is what I mean with essentially, okay? And so now these two are the same as rough paths, but X here as a canonical lift is somehow a horizontal path. It stays some attention to the unit vector, the generating vector fields, and so must be Y, and that forces n to be less equal 1. So there's a quick use of rough paths to prove a structural theorem on this log signature for PV path. Now, let's compare this result with this old result. I didn't dig out a year. I think it must be 20s or 30s, last century, obviously. So if the log Fourier transform or characteristic measure, the log of the characteristic function happens to be polynomial, then I'm sure you've heard it must be degree 2 and you're in a Gaussian situation. This is called the Marcinkiewicz theorem. And so there's some similarity here, right? So the setting, let me point it out. This is a very different setting, right? Here, there was no probability here. And there's no non-commutativity here. and yet, somehow similar in spirit. So let's take a chance to talk about moments and cumulants. And you think, okay, this is probability, part 1, maybe high school. So what's new? And surprisingly, perhaps, I do want to have a dynamic, some time evolution should be around, because we're talking about path, so naturally I want some time evolution. So let's look at the filtered probability space, and to keep things simple, I will assume all martingales are continuous. And, well, this is actually something that comes from finance. There's this good friend and co-author Jim Getherall, another person I met at Courant in my PhD days. And it went some 7 years ago. He had a very simple, an intriguing idea. He said, okay, X here. So in finance, you care about positive martingales, right? If no interest rates, positive martingales. So this is basically the exponential of X, the classical exponential of X calculus, is by definition a martingale, right? Positive martingale. And what you would like to know of that positive martingale are somehow all the powers, or equivalently, I want the moment generating, the exponential moment generating function of what people call the log price. So this quantity is of immediate interest in finance. In case z equals 1, because it's a martingale, you know what the answer is. And this all disappears. And there's much interest in understanding what is this for z other than 1, because then you know basically the law of the random variable. You can do Fourier pricing and stuff, so this is important. And it turns out there's a huge literature here when this is somehow, it has an affine structure that then you can write down that the log of this using Riccati, ODs, and there's a lot of literature. But there's something that's totally generic, granted enough. I mean, this was formal. And this is somehow this surprising, at least for me, it was surprising expansion of this form here, where this is a diamond product, or this is how Jim called it, and I will define it for you. It's very easy. So if you give me two semi-martingales, and their covariation is nicely integrable, so that this conditional expectation makes sense, then I define this as the diamond product. So you have the definition here. So even if you start with two martingales, out comes a semi-martingale, because this is the martingale part, and this is a drift that in general is not, will not vanish. A simple definition, and this is exactly the one that you want to use here. And then there's some whole expansion, remainder expansion, that satisfies a recursion that I'm going to write down in a second, a bit more general. And so this, was unclear at the time where it came from. And so this is really if you look at what's up here, let me at least drop the name. This is the cumulant generating function, but it's time little t conditional. We try to have a dynamic view on it. And so this was cleared up by switching to a more general problem. This is a paper with Jim and also a colleague of his at CUNY. We look at the joint moment generating function of, and also in finance it's very natural to look at positive martingales that you write in the form E of something, of the log price. But it's a bit cleaner mathematically to switch directly to, not to focus on this one, but focus on a simple martingale structure, right? So this is a closed martingale. You just obtain the process by conditioning here. And so I want to understand the moment generating function of this guy here at time capital T. Well, this would be the same as AT here, plus jointly with its covariation bracket. Okay, and I do it dynamically for time little t less than capital T. And again, you have this somehow an expansion of this form, G for generalized. And here is the recursion. This is more general than the one I mentioned here, but I didn't put down. So this is the generalization of. And here it is. So you may not have guessed the particular form here. I told you what this diamond is, and this works. This works in the sense of an almost sure identity for A, B small enough. Okay. So special cases. This one I find very satisfying. If this relation here holds, then you recognize here an exponential martingale. And so then this must be the answer. This is 0, and this exactly happens because this vanishes and everything vanishes. Good. The next one is if you have this relation here, then actually, if you think for a second, you're exactly in this situation here. And the last one is somehow the natural one, also clean one. When B is not 0, you're just interested in somehow in the cumulant generating function of somehow of a martingale here. Then this actually overlapped with a recent paper by Vincent Vargas and co-workers. In this case, you have a clean scaling that you otherwise don't have, then this A comes out. Okay, there are many applications, and I don't have time, and also I don't want to take sides. And let me just say that the motivation in this paper by Laguin et al. Was the Sine-Gordon model, where the time here is really somehow instead of time going to capital T here, it's more like epsilon going to 0, but you can parameterize. So there's a Gaussian field with a log kernel, and you do you mollify at some scale epsilon, and you build objects that are martingale in that mollification parameter, and then these things here help you to compute the cumulants. I'll say a bit more about this. And these cumulants play a role in the renormalization of the Sine-Gordon model. So this is a very cool application. What we had in mind with Jim was rough forward variance models. So if you have heard about you should have heard of the Black-Scholes model. The next thing you hear maybe is the Heston model. And in recent years, very popular is the rough Heston model. And it sounds like you do more and more complicated ad hoc things, but it's not at all true. And the rough Heston model, which is like the rough forward variance model, has an extremely nice structure when you write it in what's called this forward variance form, which is compatible exactly with this diamond calculus. So it fits together like a glove. It was part of the motivation here. And so it is not a finance talk, so I'll leave it like this. So just take it on face that there are many applications. And of course, you can many exercises in Revisio. You can also do alternatively with these expansions here. And so I was in email contact with Vincent. We both expressed surprise that such recursions have not been, I show a sketch of proof. It's not hard. That these have not bubbled up before 2020. This is surprising. So here's my sketch of proof. Let's start. Let's consider generics continuous semi-martingale. I'll put all integrability considerations under the carpet here, and I define here the expression of interest, the log of some conditional expectation here, okay? And I can just rewrite what's written here. So if I rewrite this, ZTT means the increment. So this is Z capital T, here it is, minus Z little t, here it is. This is just a rewriting, okay? And so this is clearly a martingale. So what you have here in the exponent is in general not a martingale, but you could look at what people call the stochastic logarithm, which amounts to take this guy here, to add a half its quadratic covariation, and that is a martingale, or at least local martingale, known as stochastic logarithm. And if you write out what the martingale condition for this object is, you find this here. And now you can recognize that this covariation or this variation bracket here, this is exactly conditional expectation. Here's the increment of the quadratic variation. So this is an example of a diamond product or square here, the way I defined it. This is where the diamond comes from. And so here you have a general relation. Okay, let's cherish it. And now you apply this to a very specific situation, namely, you replied to this guy here. So y is sorry, there's too much. There's no t here. There's no t here. So you look at y here as the martingale, and you add this here, and that's the same martingale. So that's a typo. Sorry. And then you just power count and collect. You match things in lambda, and out comes the recursion I promised. So important is it's not a good idea to expand in A or B because the scaling is not right. But the good thing is, as you can guess by scaling y, the good thing is to expand in powers of delta. Okay? So to make it watertight, this sketch is actually a bit more work is needed because this, if you want to, this analyticity here, point-wise, this is all fine, But to justify that you plug it into recursion and then expand it, you need some continuity in a space where you respect this diamond product, which is actually not so trivial. And so the better proof is not following the sketch here, but actually one where you do it in a space of finite power series where you find the log. I mean, essentially, we apply ito to the logarithm function here, right? And so you don't do it in the world of real variables, real calculus, but rather in a world of power series where truncated, they define the logarithm that you don't have any issues with this convergence, etc. So, right, let me give you a fun Markovian. I should look at the time. I should speed up here. A quick Markovian perspective, because I think it's fun. That reminds me of a talk Raghu gave many years in London at some finance meeting, actually, where he also started with a linear equation and then does a Kohl-Hopf transform, nonlinear, etc., etc. So let me do something a bit similar. I put myself in a situation where the thing, again, the purpose is here is some exponential moment generating function. I want to understand the logarithm thereof, okay? And I have some Markovian setups, so everything is somehow nicely aligned with the usual Feynman-Cass theory. And so if I want to write down the PDE, the backward PDE for this thing here, then we all know how to do this. So if L is the generator of X, then here it is. There's some forcing here. There's the terminal data that you can read off here. Now let's do Kohl-Hopf with, there's a bit of a discussion where you put the lambda. Let's put the lambda in here. And let me write down the new PDE for the log of H mod this factor lambda here. And so what you get here, and let me, for the sake of time, let me skip these details here. What you get here is basically a nonlinear PDE of HGB form. And if you're in a simple setting here with the Laplacian, then here this would just be the gradient square. More generally, you'd have the Carré-Duchamp. And this is a nonlinear PDE, okay, like KBC with smooth noise. And what you want to do is expand in lambda. So that rings a bell because Martin has shown us in great detail how to do this 10 years ago. And of course, there was much more he did. But as far as the initial analysis of the KBC equation was concerned, he did exactly these expansions here, then controlled the rest ingeniously with rough path methods. Okay? So in case you forgot how he did it, or you can do it yourself, it's not very hard, you just make a perturbative ansatz here. This is a nonlinear equation. You study it in the somehow weakly nonlinear regime where this is small. You do a perturbative expansion, and you quickly see, because of the quadratic structure here, that the good thing is to expand this in terms of binary trees. And so the labeling here is, I've copied this straight from Martin's old KPC paper. The labeling here is, when you have here a tree here, a binary tree, that you can write as the root joining of two binary trees, then UT is defined as, you take, this is how the recursive, structure works. And so you can just write this, what Martin called it a wild expansion. Here I've just rewritten it here. And then you can collect all the trees of a given number of leaves, let's say n, put them all in one bucket. And this is exactly the Kn that we had, okay? Because if you think what our Kn did, it was exactly this. And so you can line up these recursions here, actually. So the Kn was exactly the sum of these U-taus for a given number of leaves. Then every binary tree can be written as, as the root joining of two binary trees, and so they all arise in this form. So you have this equality here, and that one now you can relate to this one. Either you do it directly because this one a priori. This is from this wild sum expansion, and that this equals this one is a special case of the expansion we had, but you can also deduce it from this view here. Okay, so this is a Markovian view on these diamond expansions, and to complete the picture, there's also a Gaussian perspective on this, and this is a JFA paper 2010 by Nordin-Picatti called Cumulants on Venus Space. So you have somehow the Gaussian, the Martingale, the Markovian picture all together. Now, I have 10 minutes left, and I want to try to somehow munch these things together. So there are two names around expected signatures is one of them, and signature moments is the other one. And so let me tell you what it is. So now we need probability. So we have path as in the very beginning. And just to make sure we know what we're talking about, let's think of d-dimensional continuous semi-martingale. So we're in a comfort zone. And we can define the indefinite signature or this lifting process here the same way as in the beginning, but now we use Stratonovich integration, okay? Everything else unchanged. And the signature moment, by definition, or expected signature, is simply given by looking at the resulting process. So at time t, this is a random variable that takes values in this big tensor algebra. You take component-wise the expectations, provided they're all finite, which is, you can put conditions, there's no problem. And the resulting thing here at the fixed time t is one element in the tensor algebra. Now, as opposed to ST here alone, before you take the expectation, this here would be a random element, also in tensor algebra, that enjoys additional geometry. Be group-like because you basically, Stratonovich means you have a chain rule that you inherit, shuffle relations, group-like. By the time you take expectation, convex linear combinations, this geometry is destroyed, but you still have one element here in the tensor algebra. So the ambient space is important here. We're not doing abstract processes on Lie groups. I want this ambient space to have a linear structure where I can take this expectation, right? So the correct terminology would be somehow the one of Hopf algebras, and this G is the character group, but let's not go in there. Now, who cares about this? Well, turned out there was an initial motivation. Unsurprisingly, the first process you look at is Brown motion. And what happens when you do this here, you can compute this. I'll show you a formula in a second here. This is what motivated Terry and Victor, my good co-author and friend Nicolas Victor, 20 years ago to study what they called qubits on Wiener space. And one of the things you need is exactly this in case of Brown motion. So you can do a stochastic Taylor expansion, take expectations, and line things up. Now, once you believe in the signature moments or expected signature, it's very natural to look at the logarithm, right? It's somehow, again, we're back in this non-commutative space here. So this little star here is you can also think of it as a tensor product, and we're getting rid of it for the same reasons before. It's defined using power series calculus in the tensor algebra. Right, signature cumulants, a beautiful definition, Bonnier, Oberhauser. And let's compute. Let's have some example. I'll look at what a Gaussian martingale that I write in this form here, or a time inhomogeneous Brown motion, where you change your opinion about your volatility, but in a deterministic time-dependent fashion. Here we go. And with that, now it's a one-on-one exercise in stochastic calculus. You rewrite this Stratonovich in Ito plus something. And the nice thing about this Gaussian situation here is this covariation bracket is deterministic, and now you write the integral equation, you take the expectation, and you see what remains is a simple ODE in the tensor algebra for the expected signature. Here it is. And that's a linear ODE in the tensor algebra. It has some time inhomogeneity. Okay, that rings a bell. If you're interested in the signature cumulants, Magnus. Right? This is exactly the situation that Magnus, but now somehow in a not quite the same situation. Earlier we had here just something d-dimensional, but here now we expand it here. This is a symmetric matrix, so we're not in the same situation, but it's still in this Magnus world, and so here's how it looks like. This is the Magnus expansion for signature cumulants in this simple example. Okay, I hope we can do more than just Brown motion, but let me beat this example here to the end. If you have no time dependence and you're looking at standard Brown motion, then all these commutators vanish, okay? And then you have one very simple formula, namely this one. And that's pretty. At least I think it's pretty. It here is the identity 2 tensor. This is the tensor exponential. And here's the expected signature of Brown motion up to time t. So make no mistake, there's a lot of information in here. So in this signature of Brown motion, if you look at the second level and you fish out the right components, you have Levy area. And because you have all sort of shuffle relations that I'm not talking about, you can easily extract any power, so any moment of Levy area, you can also extract it here just by a little bit of shuffle algebra. So there's a lot of information in here. All right. So now here's almost the finale. Let's remind ourselves quickly what we could do for, in a one-dimensional case, this diamond expansions. In dimension 1, right, we had the following functional relation. This is in the sketch of the proof that I showed you. This guy here, that was the definition. You have this functional relation here. So Z is given, and this is what you want here, and this is somehow, this is quadratic. So if you expand this, you have this here, this is fine. You have this one shows up here, this one shows up here with, in a quadratic fashion here. And so if you start to iterate, which we did, then you get these binary trees, this diamond trees or hierarchy trees or whatever. So in order to make the same work for this expected, for the signature cumulants, we also need somehow functional relation now in the tensor algebra, and then just by projecting to the tensor levels one by one, we can get similar recursions. So the key is to find a similar relation here. The rest is somehow picking up the terms. And here's the answer. If you're now in the full non-commutative setting, here is the signature of a sufficient integrable semi-martingale from time little t to capital T, conditional expectation time little t. Here's the log in the tensor algebra. That gives you a process, a semi-martingale. T is fixed with values a priori in this big space, in this tensor algebra. Okay? And the following relation holds. Namely, you have, and this is why I put it here, you should compare this one here with this one here. They're all there, up, plus something else. Of course, we're in a different space here. We're not, this takes place in the tensor algebra. So when you look at the brackets here, you have to make sure you define carefully what bracket do you mean. So here's a little indication what I mean. And then there's a red term here that accounts for all the non-commutativity. And I don't have really time to drill into the details, but I'll show you, okay? But before, a few remarks here. So once you have this functional relation here, you can just, project on the tensor levels and work your way up. So this gives you immediately some expansion here. And that generalizes at the same time Magnus and the diamonds. So we were quite happy with that. If you do it in the Markovian setting, well, you can write down systems of PDEs in tensor algebra. This was first done just for the signature moments in a paper by Terry, 15. And if you like jumps and Levy processes, you can also do this. But for the sake of this talk, I chose not to. And I should give you a glimpse of how this correction term looks like. So for that one, you need more notation. You need an outer tensor covariation where you somehow keep them separately here. If this is somehow an entry on the second tensor level here, and here one of the third one, then you don't have to munch them all together, but you need to keep them separate, which is the reason why I initially wanted to work with star and not with this one. So again, if you're used to Hopf algebras, then you know the problem that you need sometimes more than just one tensor product. And then G, that's the same as the one from Hausdorff in the very beginning. Then Q is something, okay, a bit more complicated. I don't want to define here. And I mean, it's defined here, and these are all explicit. There's some combinatorial factors, but who cares? And then this expansion here you get, okay? So, good. And now, sanity check. You specialize a few examples and see that it does the trick. So one thing you can do is you can project the whole thing down from the tensor algebra to the symmetric algebra, and then by construction, all the non-commutative terms drop out, and then you get somehow a multivariate version of this diamond expansion. Okay, you could do that otherwise, but it's contained. If you try the previous example, signature cumulants for time inhomogeneous Brown motion, of course, it's an exercise, you get it. The third one is you can just apply it to a process which is a smooth path. Why not? And in that case, all the brackets disappear, and you're basically recovering the classical Magnus, but now from a backward perspective, but it's equivalent. And the last one is interesting. There's a recent paper by Martin where he looks at fractional Brownian motion, multidimensional fractional Brownian motion. And it has been known for some time when the Hurst parameter is less equal than a quarter, the thing does not, the Levy error does not converge. You can compute the variance, it explodes. So the only way to renormalize this would be to do it in a multiplicative way, to divide by let's say the square root of the variance that explodes. And if you do this, and he carries this out in great detail in a nice paper, he finds that you have convergence in law to a Gaussian limit. Namely, well, on the level 2, it's really a Gaussian limit. It's the Brownian motion that lives on the space of antisymmetric 2 tensors. So this rescaling actually makes sure that there's no component of the path left in RD, nothing. But on the second level, you're left with this Gaussian, with this Brownian limit here. And then from a rough path perspective, to understand what happens to equations here, this is naturally viewed or developed into a level 4 rough paths. And these are not usually what you see. And this fits essentially directly in our framework. So you don't have to develop. I have 0 minutes left. OK, I think I'm almost there. And this fits in the framework. I mean, almost. It fits in when you write down the theorem precisely, you don't have to develop a d-dimensional semi-martingale. You can start right away with developing a semi-martingale that lives in this Lie algebra. The development is totally fine, and so the all goes through. And if you do this, then you find that the signature cumulants here can be written down explicitly, and here they are. Okay, or this is so AI and base vectors, and on this guy here is well, it's defined here. These are the antisymmetric 2 tensors, and then you, like in the Fawcett formula, you have to square it, and that gives you a signature cumulant that happens to be a level 4 tensor. And so I ended with a conjecture, namely, so we are on it, but we're not there yet. The conjecture is, let's look at the class of processes that have a well-defined signature. Okay? So semi-martingales are usually your best friend, but they could also be GN-valued semi-martingales that you develop a la, so these are things from Le Bengle in the 70s, this development is no problem. I need the signature to be well-defined, and then sufficiently integrable that this expected signature and then the signature cumulants make sense. I want that. And now I say, OK, what if they are, in general, that's a big series. What if that series is finite, so it's a polynomial? Well, I believe that this can only happen if the law of the signature is basically the law of the signature of a Brownian rough path, but that it could be a complicated Brownian rough path like we have seen it in this higher example, that you get it from developing a Lie algebra valued Brownian motion, possibly with a drift, and in that case, the degree of this should be 2n. So that's a very precise conjecture, and if you make the effort of doing this in d equals 1, so then you fall back to a non-commutative setting. This is consistent with Marcinkiewicz, the classical one. And if you drop the probability here, then you get back to the theorem on log signatures that I had. So this is a common generalization of known things. So I believe this is true. And thank you for your attention. All best wishes to Professor Varadhan, and happy to take any questions or discuss over coffee.
Thank you very much.